Hello students, this is the first lesson I am uploading in my YouTube channel. Let me introduce myself. My name is Bhat. I am a mathematics teacher having an experience of about 35 years. I have been teaching mathematics for secondary school students and senior secondary school students, and also the students who are preparing for various competitive examinations like JEE, Karnataka CET, etc. I have already started uploading the lessons for 12th standard and Karnataka second PUC students. But this is a special lesson which is prepared on the basis of the NCERT textbook. Of course, this is useful for the students who are preparing for CBSE 12th standard, and it is also useful for the students who are preparing for PUC in Karnataka, because both systems are following NCERT textbook. But this is a special lesson which I am following exactly the NCERT textbook version, and all the examples and other things I will be selecting from this textbook only, so that definitely this will help the student in preparing for the examination. So let me start with the chapter 1, relations and functions. So lesson 1, relations. In this lesson you will learn the following things. One is types of relations. So four different types of relations are there: reflexive relation, symmetric relation, transitive relation, and equivalence relation. Then equivalence relation is actually, it is reflexive, then symmetric, and transitive. In this lesson, I will be discussing only these four important concepts. But the concept relation is not something new to you. We have already studied this. Therefore, let us first recall what we have done in the first, that is 11th standard. So these are things we have studied. Let me just recall. A definition of relation we have seen. This is the definition. Relation from a set A to another set B is subset of A cross B. So the set of element of A which are related to some element of B is called domain of the relation, and the set B is called the codomain, and the set of element of B which are related to some element of A is called the range. So these are the four important concepts. One is definition of the relation, second one is domain, then codomain, and the range. So these are the things we studied. Now let me clarify. Let us take one example. Say A equal to 1, 2, 3, 4, 5, 6, B equal to 3, 4, 5, 6, 7. Let us define the relation R equal to, we have done this type of example last year, xy such that y equal to x plus 1, x belonging to A, y belonging to B. So the relation is expressed in rule form, set builder form. Now let us first convert this into roster form. You know this method, roster form. So R equal to, when you substitute various values for x and get the value of y, you get the ordered pair like this: 2, 3, 3, 4, 4, 5, 5, 6, and 6, 7. Now it is very easy to find what is the domain, what is the codomain, what is the range, etc. Now here domain is 2, 3, 4, 5, 6, because the definition of domain is the set of element of A which are related to some element of B. So for 2, 3, 4, 5, 6, and range is, it is the set of element of B which are related to element of A. Therefore it is 3, 4, 5, 6, 7. And codomain is of course B second set is always codomain. So this is what we studied last year. Then there is another small concept which is related to this one. Here relation is from A to B. That means A and B are two different sets. But we can also define the relation from A to A only. Such types of relations called relation in A. Relation in A. And this year when we are studying types of relations, you have to remember that we are talking about relation in A only. That means it is a relation from A to A only. It is not A cross B, but A cross A only. So this is the understanding. Now let us study now different types of relations. So the relations are of following types. One is reflexive relation, second one is symmetric relation, third one is transitive relation, and the last one is equivalence relation. Now let us study one by one. So reflexive relation is the first one. Definition is this: a relation in A is called reflexive if for every x belonging to A, xx belongs to R. So this is the definition. Let me clarify this with the example. Say, let us take A equal to 1, 2, 3 and R equal to say 1, 1, 2, 2, 3, 3 and 1, 2. What we need is we need a subset of A cross A. So R is a subset of A cross A. Now, if you closely look, this is reflexive relation because you can see here 1, 2, 3 belongs to A and 1, 1 is in R, 2, 2 is in R, 3, 3 is in R. Look at the definition. For every x belonging to A, xx must be in R. So 1 means 1, 1, 2 means 2, 2, 3 means 3, 3. Therefore it is reflexive. Let us also take one more example where it is not reflexive so that the idea is clear. So A equal to, I have added one more element 4, but the relation R is same, that is 1, 1, 2, 2, 3, 3 and 1, 2. Now this is not reflexive because you see here 4 is in A but 4, 4 does not belong to R, therefore it is not reflexive. So this is the idea of reflexive relation. Now let us check our understanding with the help of some examples. First one, you see, determine whether the following are reflexive relations or not. First one is A equal to 0, 1, 2, 3. R is given. You have to check like this: 0 is there, 0, 0 is there, 1 is there, 1, 1 is there, 2 is there, 2, 2 is there, 3 is there, 3, 3 is there. So definitely first one is reflexive. Same way you can check the second one. B, A, B, C. A is there but A is not there. First element itself it is violating, so no. So you need not check the remaining. Third one, you see P, you check P, P, yes it is there. Q, Q, Q it is there. R, R, R it is there. S, S, S is there. So definitely it is yes. So this is just for understanding whether we have clear idea about the reflexive relation or not. Now let us take the next type, symmetric relation. So let me give the definition first. A relation in A is called symmetric relation if xy belong to R implies yx belongs to R. Let me clarify this one. Let us take for example 1, 2, 3 and R equal to, let us say 1, 1, 2, 2, 3, 3, 1, 2 and 2, 1. Now if you take 1, 1, if you interchange also no problem, therefore 1, 1 you need not consider, 2, 2 you need not consider, 3, 3 you need not consider. Take 1, 2, 1, 2 is there, 2, 1 is also there, therefore it is symmetric. So you can say this way: 1, 2 belongs to R and 2, 1 belongs to R, therefore it is symmetric. Let us take one example where it is not symmetric so that idea will be clear. Let us take A equal to 1, 2, 3, R equal to 1, 1, 2, 2, 1, 2, 2, 1, 1, 3. Now this is not symmetric because see 1, 2 is there, 2, 1 is there, no problem, but 1, 3 is there but 3, 1 is not there, because this is the reason: 1, 3 is there but 3, 1 is not there, therefore it is not symmetric. So this example is sufficient. Let us proceed further. Let us check our understanding. So the first one, determine whether the following are symmetric relation or not. So here you can check like this: 2, 3 is there and 3, 2 is there, so definitely it satisfies. Next, 1, 2 is there, 2, 1 is there, yes, and other you need not worry, 0, 0, 1, 1, 2, 2, even if you interchange it will be same, therefore definitely answer is yes. Now let us take one more. B, A, B, C. R is A, B, 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 C, C, A, C, C, A, B, A. Now here you can see the first element itself, A, B is there and BA is there, so it may be lost but it is satisfying. Then AC is there, CA is there, so yes, therefore definitely answer is yes. All other elements are A, B, B, C, C, you need not check. The next one is C, P, Q, R, S. R equal to P, P, Q, Q, R, R, S, S, that you need not worry. P, Q, Q, R, R, Q. So now you can check here, P, Q is there, Q, P is not there. That is sufficient. So definitely you can say no. Even if one pair is violating, then you can say no only. So this is the example. Next one, transitive relation. A relation A is called transitive relation if xy belongs to R and yz belongs to R, then xz belongs to R. That means you have to select two pairs, xy and yz. If these two pairs are there, then the xz pair must be there. So that is the idea. So let me take an example. Say 1, 2, 3 A R equal to 1, 1, 2, 2, 3, 3, 1, 3, 3, 1 and 1, 2. Now let us check like this. See 1, 3, 3, 1 is there. So 1, 1 is there. Therefore this is the way you have to check. Is a transitive relation because you have to check like this. See 1, 3 is there and 3, 1 is there. Now apply the condition xy, yz, then xz and 1, 1 is there. So definitely it is transitive. Similarly, 3, 1 is there, 1, 3 is there because you should take all possible such pairs. Therefore, checking transitive is not easy. 3, 1, 1, 3. Therefore, as per the definition, 3, 3 must be there. Yes, 3, 3 is there. Therefore, it is transitive relation. Now let us take one more example, example 2, where it is not transitive, so that idea will be clear. Let us take A equal to 1, 2, 3, R equal to 1, 1, 2, 2, 3, 3, 1, 3, 3, 1 and 1, 2. Now here we can see very clearly it is not transitive because see take for example 3, 1, 3, 1 is there and 1, 2 is there. So x, y, y, z. Now as per the definition x, z must be there. X is 3 here, z is 2. So now 3, 2 is not there in the relation. Therefore it is not transitive. Hence it is not transitive. Next, let us check our understanding with the help of a few examples. First, determine whether the following are transitive relations or not. First one, 0, 1, 2, 3. You can check like this. 0, 0, 1, 1, 2, 2, 3, 3. You need not worry. 1, 2, 2, 3, 1, 3 is there. Then no other element is violating. Therefore, definitely it is yes. Second one you see AB, BB, CC, AC. AB, BC is there, AC is there. Then no other element is violating. Therefore, definitely it is yes. You can check. The third one you can see here PP, QQ, RR is there. PQ is there, QR is there, PR is not there. Therefore, definitely it is not a transitive relation. Let me repeat again. Just check the last two elements. PQ is there, QR is there. If it is transitive, PR must be there, but PR is not there. Therefore, definitely it is not transitive relation. So these are the three relations: reflexive, symmetric and transitive. The last one is equivalence relation. Equivalence relation means definition is very simple. A relation R in A is called equivalence if it is reflexive, symmetric and transitive. So if all the three are true, then it is equivalence relation. That means a relation which is reflexive, symmetric and transitive. Let us take an example. Say A equal to XYZ and R equal to, let us take XX, YY, ZZ, because it should be reflexive. So XX, YY, ZZ. Then XY is there and it should be symmetric also. So YX. So this is equivalence relation you can check because symmetric also, transitive also. Therefore, it is an equivalence relation. So 1, let us verify like this. It is reflexive because XX is there, YY is there, ZZ is there. It is symmetric because XY is there, YX is there. It is transitive because XY, YX pair is there, XX pair is there. YX, XY pair is there, YY pair is there. Therefore, it is equivalence relation. Next, there are two more relations which we have studied last year. A relation is called empty relation if if R equal to pi, because pi is the subset of every other set. Therefore, pi is a subset of A cross A. Pi is also a relation which is called empty relation. Similarly, a relation is called universal relation in A if R equal to A cross A, because A cross A itself is subset of A cross A. And definition of relation is subset of A cross A. Therefore, A cross A is also a relation. that relation is called universal relation. So these are the two extreme relations. One is the empty relation or void relation. Second one is universal relation. So let me sum up now. We have studied four types of relation: reflexive, then symmetric, then transitive, then equivalence relation. Now, let us take a few examples on relation so that idea will be clear. The first example, let A be the set of all students of boys school. Show that the relation R in A given by R equal to AB such that A is a sister of B is an empty relation. It is a very simple example, but it is an example of empty relation. You have to give the reason like this. Since the school is boys school, no student of the school can be sister of any other student. That means R cannot have any element. So therefore R is a empty relation. So this is the uh, reason. Let me take the next example. Example 2. Let A be the set of all students of a boys school. Show that the relation R in A given by R equal to AB. The difference between any two students A and B is less than 3 meter. Difference in height. Difference in height between any two student is 3 meter. Definitely it is universal relation because, see, the reason is this. It is obvious because the difference between any two students height is always less than 3 meter. Height here it is. So hence R is universal relation. So this is the idea. So there is one sentence, a word missing, difference between the heights of the students. Next, example 3. Let T be the set of all triangles in a plane. Let R be a relation in T given by R equal to T1, T2. That means T1 and T2 are two triangles such that T1 is congruent to T2. Then show that R is equivalence relation. R is reflexive because, see, this is how we can prove. For any triangle T belonging to T, T is always congruent to T. This implies TT belongs to R. So this means R is reflexive. And this is the way you have to write also. This is the method of writing a reflexive relation, symmetric relation in general. Similarly, now we can show that R is symmetric. What you have to do is, suppose T1, T2 belongs to R. This implies, what is the definition now? T1 is congruent to T2 because the definition of relation is T1, T2 belongs to the relation if T1 is congruent to T2. Now, whenever T1 is congruent to T2, naturally T2 is also congruent to T1. You know this from geometry. So this implies T2, T1 also belongs to R. So it is symmetric relation. Then R is transitive. Let us take, for example, T1, T2 belongs to R and T2, T3 belongs to R. This implies, first one says T1, T2 belongs to R means T1 is congruent to T2. Similarly, T2, T3 belongs to R means T2 is congruent to T3. This implies T1 is congruent to T3. Therefore, T1, T3 belongs to R. Therefore, R is transitive. Thus, it is reflexive, it is symmetric, and it is transitive. By definition, R is therefore equivalence relation. So this is the third example. Next one, example 4. Let L be the set of all lines in a plane and R be the set of relation in L defined by R is set of all lines L1 and L2, ordered pair L1 and L2, such that whenever L1 is perpendicular to L2, so that is the relation. Now show that R is symmetric but neither reflexive nor transitive. So let us prove like this. R is not reflexive because, you see, you take any line L belonging to the set of lines. No line can be perpendicular to itself. L cannot be perpendicular to itself. This means what? L cannot be in R. So this means R is not reflexive. Next, why it is symmetric? Let us take, for example, L1, L2 belongs to R. By definition, it implies L1 is perpendicular to L2. Whenever L1 is perpendicular to L2, naturally L2 is also perpendicular to L1. So this implies L2, L1 also belongs to R. So this means R is symmetric. Now we have to show that it is not transitive. See, we can prove like this. See, suppose you take L1, L2 belongs to R and L2, L3 belongs to R. Suppose it is transitive, what should happen is L1, L3 should be in R. But this is not possible. We can show L1 is perpendicular to L2 because L1, L2 belongs to R. Similarly, L2 is perpendicular to L3 because L2, L3 belongs to R. Now look here. If L1 is perpendicular to L2 and L2 is perpendicular to L3, in the diagram it is very clear. L3 will be parallel to L1. So it cannot be perpendicular. This implies L1 will be parallel to L3. This means L1, L3 cannot belong to R because condition is perpendicular. Therefore, R is not transitive also. So R is not transitive. Therefore, the given relation is only symmetric, but it is not reflexive and it is not transitive. Next example. Show that the relation R in the set Z of integers given by R equal to set of all ordered pair EBs that 2 divides A minus B is an equivalence relation. 2 divides A minus B. Now, first R is reflexive because see, suppose you take A belonging to Z, that means A any integer, then A minus A is 0, you know that, and 0 is divisible by 2. This implies A belongs to R, so R is reflexive. That means for every integer A minus A is 0 and that 0 is divisible by 2. So by definition, therefore, A should be in R. Next, R is symmetric because let us say, for example, AB belongs to R. This means what? 2 divides A minus B. Similarly, 2 divides B minus A also. Whenever 2 divides A minus B, it divides B minus A also. So this implies BA belongs to R. So this means R is symmetric. Then R is transitive also we can prove. Let us take, for example, AB belongs to R. This and BC belongs to R. This implies 2 divides A minus B and 2 divides B minus C. This implies 2 divides A minus B plus B minus C, that is 2 divides A minus C. So this implies AC belongs to R. So what did we achieve here is AB belongs to R and BC belongs to R implies AC belongs to R. So R is transitive. So here now you can see it is reflexive, it is symmetric and it is transitive. Therefore, R is an equivalence relation. So this is the fifth example. Let us conclude here. Let me revise what we have done. We have taken types of relations: reflexive, symmetric, transitive, 3 different types. Then if a relation is all the 3, then it is equivalence relation. Then I have taken a few examples to clarify the concept. In the next lesson, let us continue with the examples on relation. Hope you like this video. Please subscribe my channel and I will be uploading all the lessons related to all the chapters. Of course, it may take some time, but definitely I will be completing this task. So please subscribe and share with your friends so that it will be an encouragement for me and to do it in a better way. Let us meet in the next lesson with examples on relations. Till then, bye. Take care.